Hello everyone, welcome back to my channel. Today we have a very interesting topic and most of the students requested me for this particular topic. It is di and polyprotic acids and di and polyacidic bases. So di and poly, as the name suggests, di means two, acid means which gives H plus ions. So some of the acids, like see, we have oxalic acid or even sulfuric acid, they even phosphoric acid H3PO4. So these acids will give more than one H plus ions in their solutions, means there are more ionizable protons. Okay, for example, oxalic acid. So oxalic acid, when it is dissolved in water, it will give 2 H plus ions, leads to the formation of oxalate ion and gives 2 H plus ions. So that means it is diprotic acid. It gives one at a time, that we will discuss later on, but any acid which gives 2 protons, 2 H plus ions, that is called dibasic acid. If it gives 3, like H3PO4, it gives 3 H plus ions, so it is tribasic acid, and so on. Any acid which gives more than one, that is polybasic acids, di, tri, tetra and all, these are called polybasic acids. I think you got an idea that what is dibasic acid, which gives 2 H plus ions, what is tribasic acid, which gives 3 H plus ions, and tetrabasic and so on, polybasic, which gives more number of H plus ions. If it gives only one H plus, that is called monobasic acid. So these are called polybasic, or sometimes we can call it as polyprotic. Same meaning is same. Polyprotic means which gives protons. Poly means more number of protons. Okay, many protons, that is called polybasic acids. Okay, done. Same if we talk about di or polyacidic bases. See, NaOH, how many OH negative ion it will give? Obviously 1. So it is called monoacidic base. If we have calcium hydroxide, it is diacidic base. If we have AlOH thrice, it is triacidic base, means if the base gives one OH negative ion per molecule, that is monoacidic base. If it gives 2 OH negative ion, it is diacidic base. If it gives 3 OH negative, it is triacidic base, and so on. Many number of OH negative ions if it gives, it is called polyacidic base. Di, tri, so on, they are all under the category of polyacidic bases. So this is the definition of dibasic, tribasic, okay, acids or diacidic, triacidic bases, and polybasic acids, polyacidic bases. Now, if we see the ionization reactions for a dibasic acid, like we have H2X. So H2X, if it has aqueous solution, then first it give one H plus ion and HX negative, then HX negative aqueous, that give H plus and X2 negative. Got it? Because one H plus ion, when it is removed from H2X, we get H plus and HX negative, and when we have HX negative, it give H plus and then negative charge, now it is twice, 2 negative. So these are reactions for the ionization of dibasic acid. Means one H plus ion is removed at a time. That is first step. This is step 1 and this is step 2. Now if we write their equilibrium constants, then for first one, let us say this is Ka1 and this is Ka2, first dissociation constant and second dissociation constant. So what is Ka1? Ka1 is equal to H plus ion concentration into HX negative ion concentration, because you know dissociation constant of acid or any equilibrium constant, that is equal to product of the concentration of products divided by product of the concentrations of the reactants. So it is H plus ion concentration into HX negative ion concentration divided by H2X concentration. Now Ka2. So what is Ka2 now? It is H plus concentration X2 negative ion concentration divided by HX negative ion concentration. So this Ka1 is, it is first dissociation constant of acid H2X, and this is second dissociation constant of H2X. First dissociation constant and second dissociation constant, because in first step there is removal of first H plus ion, in the second step there is a removal of second H plus ion. So could you figure out which H plus ion is easier to remove? So if yes, then it's okay. Otherwise I let you know now. You know H2X is a neutral molecule. So removal of H plus ion is easier because it is easier to remove H plus ion from a neutral molecule. But if you see in the step 2, we have already an anion. When we have an anion and we have to remove positive ion, H plus ion, we have to remove. So to remove H plus ion from already formed anion, it is difficult. Reason being, there is an electrostatic force of attraction between positive ion and negative ion. They attract each other and therefore removal becomes difficult. That's why keep in mind that higher dissociation constants are always less than the lower dissociation constants. Even if we have a Ka3, means we have tribasic acid, then in that case always Ka3 is less than, irrespective of the acid, whatever acid we have, first dissociation constant is always greater than second, second is always greater than third, and so on. Higher dissociation constants are always less, because when H plus ions are removed, negative ions goes on increasing, and therefore electrostatic force of attraction between H plus and already formed anion, that goes on increasing, and therefore it is increasingly difficult to remove H plus ion. I hope you understood. You are getting along with me? So in this way, there is Ka1 and Ka2. They are called first and second ionization constants respectively of the acid H2X that we have already discussed right now. Similarly, if we have tribasic acid like H3PO4, now we have three ionization constants. So see, I will write here only H3PO4. So when its aqueous solution is taken, first we remove H plus sign, so it becomes H2PO4 negative. So dissociation constant associated with it is Ka1, and it is equal to H plus sign aqueous H2PO4 negative aqueous divided by H3PO4. Then H2PO4 negative, that will give H plus aqueous plus HPO4. Now it becomes 2 negative. So Ka2, that is second dissociation constant, and it becomes H plus ion concentration HPO4 2 negative concentration divided by H2PO4 negative ion concentration, and then HPO4 2 negative, that will give H positive and PO4 3 negative, and that is Ka3, third dissociation constant, and it is H plus ion concentration PO4 3 negative ion concentration divided by HPO4 2 negative ion concentration. And same, it is easier to remove H plus ion from the first one. It is difficult to remove from H2PO4 negative because it is already an anion, and it is more difficult to remove from the HPO4 2 negative because there are two negative charge on the anion, and therefore Ka3 is always very less than Ka2 is very less than Ka1. So main contribution of H plus ion is from Ka1. In the first step, maximum number of H plus ions are formed. So sometime if alpha Ka3 is very less than Ka2, both are very less than Ka1, so what we do, we take H plus ion concentration from Ka1 only and get pH. That we will discuss later on, but now at present you will keep in mind that Ka3 is always, means higher dissociation constants, they are always very less than the lower dissociation constants. So already I have discussed with you, it is more difficult to remove a positively charged proton from a negatively charged ion because there is an electrostatic force of attraction between the cation and anion, and it is more difficult to remove a proton from a doubly charged anion. See, this can be seen in case of removing a proton from the uncharged H2X as compared to from negatively charged HX negative, and it is more difficult to remove a proton from a doubly charged. Okay, if we take into account H3PO4, then in case, this can be seen in case of removing a proton from an uncharged H3PO4 as compared to from a negatively charged H2PO4 negative. Similarly, it is more difficult to remove a proton from a doubly charged HPO4 2 negative anion as compared to HPO4 negative. Okay. Now, what are the factors which affect the acidic strength? There are always a question, why some acids are stronger than the other, and what are the factors which are responsible for making one stronger and other weaker. So why one acid is strong, other is weak? Like we say H2SO4 is a strong acid, HCl is a strong acid, but H3PO4 is a weak acid. So what is the reason behind it? That we are going to discuss now. See, it is a very complex thing, but to make it simple, we take into account only two things. First is bond strength and other is polarity of the bond. See, if we have three atoms are there and bond length is increasing. If bond length is increased, what happened? Bond strength decreases. Obviously, as bond length increases, bond strength decreases, and if bond strength decreases, bond becomes weak, and therefore it is easier to remove H plus. That means weaker the bond strength, weaker the bond, stronger is the acid. Second thing is polarity of the bond. If bond is more polar, like more positive and negative charge, more positive charge, more negative charge, so they can settle complete positive, complete negative if polarity is increasing. So decrease in the bond strength or increase in polarity, both will favor the increase in acidic strength. I am repeating once again, decrease in bond strength, that will make H plus ion removal easier. Second, increase in polarity of the bond, that will also enhance the removal of H plus ion. In both the cases, acidic strength increases. Okay, so let's go to the next slide. That when strength of the bond decreases, what would happen? It is easier to break the bond, and therefore that particular acid becomes stronger acid. And if the bond is more polar, then what happened? Obviously, electronegativity difference, if it is more, then polarity increases, and if electronegativity difference is more, then H can donate electron to the atom attached to it, because that atom is more electronegative, that will attract the electron strongly. Bond pair is attracted more towards the atom attached, because being more electronegative, it attracts the shared pair, and therefore hydrogen is forced to give its electron to that particular atom, and therefore H as a plus ion is removed, and that is what? An acid, because acid is one which can give H plus ion. So increase in polarity, decrease in bond strength increases the acidic strength. But when we take into account bond strength and when we take into account polarity of the bond, because sometimes what happened, both are increasing or both are decreasing, or here we are saying that acidic strength is directly proportional to polarity of bond and inversely proportional to, yes, but inversely proportional to strength of bond. So keep in mind, when we compare elements in the same group, like we have H2O, H2S, NH3, PH3, ASH3, SBH3, H2SC, H2T, or HF, HCl, HBr, HI. That means if we compare the acidic strength among elements in the same group, then we take into account the bond strength, because that is the dominating factor. So when we go down the group, you know, as we go down the group, what happened? Size of atom increases. If size increases, hydrogen element bond strength, element bond length increases, and hydrogen element, if bond length increases, bond strength and bond length are inversely proportional, so bond strength decreases. So it is easier to remove H plus ion because energy required to break the bond is less now, and therefore acidic strength increases. So keep in mind, as we go down the group, acidic strength increases among hydrides. Hydrogen means there are only two atoms, hydrogen and other atom. Okay, now come to when we are going along the period. Along the period, for example, we have methane, ammonia, H2O, HF, or SiH4, PH3, H2S, HCl. So as we go along the period, then electronegativity of the element is a deciding factor. Polarity of the bond decides, because along the period electronegativity is dominating factor. Okay, so along the period, what happened? Electronegativity of element increases. As electronegativity increases, so polarity of the bond increases, and so is the acidic strength. So acidic strength increases. So that's all about this topic. Now see, if we go down the group and we take into account electronegativity, so you know, down the group electronegativity decreases, so polarity of the bond decreases. So what we call, if we talk about polarity of the bond, acidic strength should decrease, but here is the trick. As we go down the group, size is dominating over electronegativity. Size is dominating, keep in mind, size is dominating, and that's why bond strength play the major role while deciding the acidic strength. Okay, and when we go along the period, size decreases, so hydrogen element bond length decreases. So what do we call? Bond strength increases, acidic strength should decrease. But again, there is a trick that if we go along the period, we take into account electronegativity, and electronegativity along the period increases, and that will increase the polarity of the bond, and therefore what happened? Acidic strength increases. So in case of hydrides, we go along the period or we go down the group. Acidic strength increases on both sides, because down the group bond strength decides, along the period electronegativity, or we can say polarity of bond decides. Down the group bond strength decreases, that's why acidic strength increases. Along the period polarity of the bond increases, and that's why acidic strength increases. But it is true for hydrides only, so keep in mind. Thank you so much for watching this video. Do like, subscribe and share my channel. God bless you all. Happy learning. Jai Hind, Jai Bharat.